sessions, and then I make the recording available to the student 3 or 4 hours after the session because it takes that long to process.
Right.
And I would be happy to do that if you want to give me your email address before we're finished here.
Sure. Well, you have it from the email earlier, don't you?
I do. Yes. I will send I will send you a link to that email that will show you where you can watch a recording of this session. It's in YouTube format, so you can pause it or fast forward it or reverse, whatever.
Okay, awesome.
Yeah.
All right, then can we just jump right into it?
Sure.
All right. I guess we could just go down the list of the problems.
Yeah, go ahead.
Some of these I know how to do. Some of them are a little more confusing.
Okay.
First problem: estimate the limit numerically as x approaches -1. The limit of x squared plus 2x plus 1 all over x plus 1.
Okay. Limit problems are never difficult if it's a number over a number or a number over 0 or 0 over a number.
Right.
You can substitute it directly in whatever you come up with. The only time they're a problem is if it's 0 over 0.
Right.
And that's what this produces. If we substitute -1 for x, we get 0 over 0. So we have to manipulate this first. Well, one of the ways of solving limit problems is to factor the numerator.
Right.
What's the numerator factor into?
Well, looking at this, I'm going to want one of the factors to be x plus 1, right? So the bottom cancels?
That's good thinking, yeah.
Okay.
That's always a good way to start factoring, actually.
Mm-hmm.
Knowing what one of the factors probably is.
Right. Okay, so that is x plus 1 and x plus 1?
Right. So I can now cross that out with that. And I'm left with x plus 1. And now when you substitute -1 for x, you do get a number.
Mm-hmm.
And it's 0.
Okay.
So that limit is equal to 0, which is way different than 0 over 0, which 0 over 0 could be anything. It could be a number, it could be infinity, it could be a lot of different things.
Right.
Okay?
Okay, then. The next one is as the limit approaches infinity. And the problem is 3x squared plus 3x minus 4 over 4x, I'm sorry, looking at the wrong one, minus 4 over 2x squared minus 7x. Now, if I'm not mistaken, when the highest exponents are the same and the limits to infinity, you take the leading coefficients, correct?
The ratio of that, correct. So this is 3 over 2.
Yes, 3/2.
Yeah, as far as end behavior goes, whenever x is going to infinity, the only term you really need to pay attention to is the highest exponent term.
Right.
These become insignificant compared to the big one. And so we can basically eliminate that and just deal with that. And then the x squareds divide out, so you're left with 3 over 2.
Okay. All right, then. Once again, limit numerically as x approaches -infinity this time. And the limit of x cubed minus 3,000 x squared over 4x cubed plus 8,000.
Okay.
So in this case, is when the limit is approaching -infinity,
It's not as clear that it's 1/4.
Right.
So let's look at doing this a different way. If we forgot that rule, what I can do is divide every term in this relationship by x cubed. So that's valid to do mathematically. Because you can always divide top and bottom by the same quantity. And now, if I take the limit of this as x goes to negative infinity, notice that these terms go to 0.
Okay.
These terms, this goes to 1, this goes to 4, so the limit goes to a positive 1/4.
Okay, that makes sense.
Yeah, it's the same logic that I could have used in the previous problem, where instead of just taking the ratio of those coefficients, I could have divided every term by x squared. In the previous problem, I think the largest term was x squared. And if you do that, you always get down to a situation where these terms have some power of x in the denominator, which means as x goes to either positive or negative infinity, this term goes to 0. In other words, this term's always going to go to 0, same with this term. Whether the denominator is going to positive infinity or negative infinity. And in these terms here, the x's cancel, so you're really left with a number, 1/4, and it doesn't really matter whether x is going to positive or negative infinity.
Okay, that makes sense. All right, the next one's another limit problem. This one, not as straightforward. It's the limit as x approaches 5 of e to the x minus 5. The exponent is x minus 5.
With straight substitution, what do you get?
1.
That's it.
All right.
In other words, straight substitution always works unless you get an indeterminate answer like 0/0 or infinity over infinity or infinity minus infinity, something that can't be determined on its own.
Okay.
But in this case, a direct substitution, any number to the 0th power is 1, including that.
Right.
That always surprises people.
Yeah.
But it's true.
Okay, so this next one has a graph. Would it be easier if I just emailed you a screenshot real quick, or what would work best?
Why don't you read the problem and let me see what they're looking for.
Okay, the graph of f is given. Use the graph to compute the quantities asked for if a equals 4, and a is just the increment on the graph.
Right.
And it wants the limits of 1, 2, 3, 4, 5, 6 different areas.
So my guess is it's a piecemeal function, something like this. And this would be A. May not look like this, but it's a function that it's not easy to figure out what the limits are.
Right.
Probably sounds like you need to send me a picture of that.
Okay. Then in that case, do you want it just emailed to you, or?
Yeah, if you email it to me, I'll have it on my computer and we can bring it up. Whereas
Okay, that works perfectly.
yeah, if you send it to my phone, it would take an extra step. So if you can email it, you have my email address, right?
Right, yep.
Okay.
1 second.
Boy, the technology is a beautiful thing.
Yeah, it is.
We could have only dreamed
Imagine
of doing this 10 years ago.
Yeah, it wouldn't be possible.
No. No.
Okay. All right, I just sent you the screenshot.
Yeah, I heard it. It came into my phone. It's always amazed me that it comes to my phone quicker than it comes to my computer. There it is. All right. Okay, if we look at that graph, A is the grid that would normally, I suppose, be 1. In this case, A is 4.
Right.
Okay, so when they say what's the limit of f of x, they're really saying what's the limit of y.
Right.
As x approaches 8. Can you see my cursor?
Yes.
Okay, there's 8. If A is
right
4.
there, the limit is 0, correct?
Correct.
Okay.
Okay, and then what's the limit of this function as we approach 0 from the right side? And the way to look at doing this is go to the right of 0, go to your graph, and hone in on 0. So what y value are we narrowing in on?
8.
Uh-huh. And as we approach 0 from the left side, we go to the left, go up to our graph, and we hone in on whatever point this is.
-4.
Correct. So what's the limit of f of x as we approach 0?
When there's two separate limits, does that mean there is none?
Correct. A limit only exists if the limit from the left is the same number as the limit from the right. And then you can talk about the limit as we approach 0. But in this case, they're different. One is plus 8, the other is minus 8. Since they're not the same, this limit does not exist.
Okay.
And then what is f of 0?
It would be 8, correct?
Correct. It's the closed loop dot there.
Okay.
Okay. And that last one looks like the limit of f of x, and I can't read the rest of it.
-infinity.
As x goes to negative infinity?
Which I believe it'll approach infinity because it's going up.
Right. This arrow means that that goes forever in that direction.
Okay.
So as we go negative infinity on the x-axis, y is just going up and up.
Okay, cool.
Okay.
All right, then moving on to the next one.
Okay.
Got another. Well, I guess I have a pretty good handle on limits from the graph. Maybe we can move on to something that's not as graphical.
Okay, let me just give you one test.
Okay.
Here's a function. What's the limit of this function as we approach 3 from the left? In other words, what's the limit of f of x as we approach 3 from the left?
Would it be 4?
Okay. What is it as we approach 3 from the right?
Is that also 4?
Okay, so what is it as we approach 3?
Would it just be 4?
And what is f of 3?
It would be that second dot, which would be at 2.
Correct. Okay.
Okay.
If you can answer those questions, you're probably fine with graphs and limits.
Okay.
Because this is the only one that's a bit strange, that the limit is here even though the value at that number is actually there.
Right.
So this is the only limit problem that really can not make sense to some people. But it sounds like you got a good handle on it.
Yeah, graphs are a little easier than some of the other stuff that goes on in this class.
Yeah.
Okay.
Yeah, welcome.
The next one is also...
Welcome to calculus.
Yeah.
Calculus is definitely a couple notches higher than any math that you get prior to calculus.
Mm-hmm. Oh yeah, this has been a very difficult course. This one also has a graph. I'm just gonna send you another screenshot real quick.
Okay.
Here we go.
Do you have an iPhone?
I have an Android.
Really? You have an Apple computer but an Android phone?
Yeah, well, after owning the Android for a little while, I decided there was no way I wanted anything other than an Apple computer. So.
Oh, okay.
Yeah, hopefully next phone will be an iPhone.
I have an Android also. I don't mind them. Actually, I've heard good things about the what is it? The Samsung Galaxy S4.
Yeah, they said it's supposed to be better than the iPhone.
My son has had both, and he raves on this Galaxy S4.
Wow.
It's the greatest thing since sliced bread. So, so this looks exactly the same, only instead of A, it's 1.
Mm-hmm.
Okay, so we're determining whether this is continuous on its domain.
Mm-hmm.
You know the definition of continuity? The working man's definition? It's if you don't have to pick up your pencil to graph it.
Oh, okay.
That's not the exact mathematical definition, and maybe you need to know that also. There's like 3 conditions that need to exist for continuity to be, but basically, if I were to try to graph this, I'd get this far, and then I would have to pick up my pencil.
Right.
I can't finish it without doing that. So it's not continuous at x equals 0. Which
Okay,
is
because it has 2... Because there's a different limit from the left as from the right.
Well, there's more to continuity than that. In other words,
Well, I'm sorry, I was asking for the answer below. Just one of the options is.
Oh, okay, okay. So first of all, yeah, that's not continuous.
Mm-hmm.
And if it's not continuous, say why. Because, let me just read this. Well, can't be this.
Right.
Because that's not what they're talking about. The discontinuity happens inside the endpoints, not at the endpoints. The limit of f of x is not equal to f of 0, but there is no limit of f of x as x goes to 0. Right. So it does not exist. So something that can't exist can't not be equal to that. So it's not continuous, so the only answer would be this. So they're saying that the limit, because it's not the same from the left or the right, it does not exist. However, that's not the whole story. In that previous example, that's not continuous either, and yet the limit from the left is the same as the limit from the right.
Right.
But it does not equal f of a. In other words, for something to be continuous, The limit from the left has to equal the limit from the right, and the function evaluated at that point has to equal that limit. Whereas in this case it would not be. This one was 2. Both of those limits were 4. And so this would not be continuous based on that. So I'm not real fond of their answer here. That's not a good enough. I guess that is a good enough reason. That reason would not suffice if you were faced with this graph, but it suffices with this graph.
Okay, that makes sense. All right then. Moving on to something a little different. This is something that confuses me. Okay. It's use a graph or f of some other method to determine what, if any, value to assign to f of a to make f continuous at x equals a. And the function is x squared minus 14x plus 49 over x minus 7 when a equals 7.
Okay, these are almost always factoring problems.
Okay.
So what does the numerator factor into?
X minus 7 and x minus 7.
Okay. So now the x minus 7's cancel, and we're left with x minus 7. So f of x is equal to x minus 7. Now, what again were they asking?
What value, if any, to assign to f of a to make f continuous at x equals a?
Okay. If I graph this, whoops, x minus 7, that's our function. It's got a slope of 1, has a y-intercept of minus 7. The thing is that there's a hole in this graph also.
Mm-hmm.
And that hole comes at x equals 7.
Right.
Because from the original function, there's going to be a restriction on the denominator that x can never be 7, whether or not you factor it out or not. In other words, when I say this original function equals that function, it's not quite right. This original function equals this function with the provision that x can never be 7.
Okay.
And hence that hole. So if I graph this thing and I have a hole there, well then it's not continuous. So f of, their question again is, what does f of a have to be?
Mm-hmm.
When a approaches 7 or when a is equal to 7?
When it says when a is equal to 7.
Because there's nothing that can make this graph continuous.
Okay, so the value would be none.
Correct. In other words, the moment I'm looking at what I have circled here, I have a function that is x minus 7 and x can never be 7. So if x can never be 7, I've got a hole there. And even if I were to say f of a is up here or f of a was down there, that doesn't make it continuous. I suppose if f of a was equal to that, that would make it continuous, but x can never be 7. So I don't know how f of a could be 0.
Okay. I mean, according to this, it said the answer was 0.
Okay. Well, that fills in that hole, because as a goes to 7, f of a would be 0, That's a tricky question there.
Yeah.
I mean, I don't really like the question because f of a can't be 0
Right.
as a goes to 7. A cannot go to 7. We have a provision on this function that restricts x from ever being 7. Now, if it approaches 7, I don't know. I don't really like that question. I'm not sure you can make that function continuous.
Yeah,
But I understand their answer as to why it's 0. In other words, this hole in my function occurred when x was equal to 7 and the function was equal to 0. So they're saying, okay, so when you get to that hole, if you make that f of a equal to 0, it closes up that hole, and now you have a continuous function. All right.
Okay.
I guess, but you've violated the domain. So,
Yeah. Okay. Well, the next question's pretty similar. Determine what, if any, value to assign to f of a to make f continuous at x equals a. F of x is equal to x over 6x squared minus x at a equals 0.
okay. Again, it's a factoring problem. So let's factor this to simplify it. What can we do with the denominator?
Can we take out an x?
Correct. So we're left with 6x minus 1. And now we still are faced with the domain restrictions. X can still not be 0, and it also cannot be 1/6, because that would make this term 0. So we've got x can't be 0, and x can't be 1/6, but we can still reduce this function to 1 over 6x minus 1. So now we have f of x equals that, and we can tell that this is going to have a hole in it at x equals 0, and it's going to have a vertical asymptote at x equal 1/6. So if I were to try to graph this thing, this is a hyperbolic function. So I know that there is a vertical asymptote at 1/6, and this thing probably graphs something like that. And it's still going to have a hole at 0, right there.
Right.
Okay? So when they say, wow, I hate this question worse than I hated the last one, because there's no way to get around that vertical asymptote. You can't make this. You can make it continuous if you let this be filled in, that hole there. But there's no way you're bridging this vertical asymptote at 1/6. So the question again says, what does f of a have to equal for it to be continuous, the whole function? I would say you can't do it here. You could make the left part of this continuous in the same way we did with the last problem, by letting
if we were to solve that, we'd plug in the 0 where x is, and we'd just get -1.
Yes.
Okay, I think that's the answer they're looking for.
Probably is. Probably.
Yeah, it is. It's -1.
In the same sense that they were looking for that in the last one. In other words, there's nothing we can do about this discontinuity around the vertical asymptote. You can't. Those are inviolable, whatever the word is. Okay.
Okay, then. The next one is also on discontinuity.
Okay.
But it's just saying find all points of discontinuity of the given function.
Okay.
And it has where g of x equals two separate functions.
Okay.
G of x equals... I'm sorry?
It's a piecewise function?
Yes.
Okay.
So, the top function is 2 minus 2x if x is less than or equal to 1. And then the bottom function is 2x minus 2 if x is greater than 1.
Okay. When x is less than or equal to 1, it's this function right here. So that function has a slope of minus 2 and a y-intercept of 2. So something like that. It continues on. And at x equal 1, y is 0. Let me redraw this a little bit better, since I'll call this 2 up here. Now, there's our function there. Only I don't want this part of it here because it ends right there with a closed dot. And now, to the right of 1, I've got 2x minus 2, which has a similar steep slope, only it's positive, and it goes through the point minus 2. So if it was not restricted, I would draw a straight line through there, but my straight line is now going to be like that. So there's a graph of our piecewise function.
Okay.
And you can tell that when x is equal to 1, we don't have a discontinuity. We have a continuous function this whole way. So the question is what?
The question is find all points of discontinuity of the given function. If a quantity does not exist, enter does not exist.
Does not exist. There's no discontinuities with this.
Okay.
There would be a discontinuity if they weren't the same value at the number 1. In other words, if this looked slightly different, say it looked like this, now there's a discontinuity at 1. But since they both are equal to the same thing at 1, then I don't have to lift up my pencil to draw this.
Okay. That makes sense. All right, well, let's try that again.
Okay.
The next problem is the exact same thing. All points of discontinuity of a piecewise function. This time there's 3 of them.
Okay.
Top one is 6 minus 3x. If x is less than or equal to 2. The second one is x plus 2 if x is greater than 2 but less than 5.
Let me write that different. That doesn't look good. Let me write it like this. Okay.
And the third one is x squared minus 18 if x is greater than or equal to 5.
Okay. I could graph each of these out just like I did the last one. But the important thing is there a discontinuity at our breakpoints? In other words, one breakpoint is the number 2, the other one is the number 5. There's clearly no discontinuity to the left of 2. In other words, x can go to negative infinity and y would go to positive infinity.
Right.
Okay. So what happens at 2? Well, this one is equal to 6. I'm sorry, 6 minus 6, 0. And this one is equal to 4. So those 2 points can't come together. To illustrate this, let me go ahead and graph it. Well, the first function is something like this, the closed dot, because it can be equal to 2, and it's still this function. And then from 2 to 5, it's x plus 2, which if I were to plot that, it would go through that if I were to plot it all the way, but otherwise it's going to have a slope of 1 with an open dot there. Notice the discontinuity. And then if I see what's happening at 5, well, this one is going to be 7. This one's going to be 7. So let's take this line up to just 7. Sorry about overlapping. That's the one problem with my limited screen size there.
That's okay.
So what did we decide that was? That was 4. This is 7. And then the third part of the function is x squared minus 18, which is a parabola that's been shifted down by 18. So it would look something like, let's see, the normal parabola would be like that. So this would be all the way down and then coming up like that. Only this point and this point are the same thing. So my parabola, because they're both equal to the number 7, so my parabola actually shoots up from that same end point of the middle part of my piecemeal function. So in other words, there's no discontinuity there when x is 5. Notice that I go from 7 to 7. So I don't have to pick up my pencil to finish drawing that third part of the function. The only place I have to is right here. So the only discontinuity is at x equal 2.
Okay. That makes sense.
The piecemeal functions and discontinuities and stuff, if you graph them, then you can almost always figure it out. But you don't always have to graph them if you just, in other words, I could have done this without graphing by just checked what this value was at 2. That's equal to 0. And what this value is at 2, well, that's equal to 4. Well, it can't be 0 and 4 at the same time unless it's discontinuous. So I would know there's a discontinuity just by doing that algebra. And by the same notion, if I analyze what's going on at 5, this one's equal to 7, this one's equal to 7, so they're on the same point at that break point. So it would be continuous there, and I could figure all that out without actually graphing it. I'm not sure what your intention for today was. I do offer a free first session for the first session for people, and it's a half-hour session. Sometimes I'll get calculus students that'll want more than a half hour, and they'll like want an hour and a half, and then I'll just charge them for an hour.
Okay, could we do that?
Sure, that's fine. Yeah,
Okay,
we can go to whatever ending point you want, and then I'll just charge you for everything minus the first half hour.
Okay, perfect.
All right.
All right.
So are you still pretty much on just limits and continuity? You haven't gotten into differential calculus yet?
No, we have. I'm just on the first half of the review.
The review material? Okay.
Yeah.
So you've had the power rule and the product rule and the quotient rule and the chain rule and all of that?
Yep, all that good stuff.
Okay.
All right.
Limits really is the concept that separates calculus from all of the math prior to it.
Yeah. Yeah, a lot of time on limits and derivatives.
Yeah, but once you get by limits, then the rest of calculus tends to all be differential or integral calculus.
Yes, integrals are definitely.
Yeah, you don't so much focus on limits anymore. Once you get by them the first time.
Okay, I guess then we'll just move on to some simple derivatives.
Okay.
This one is a word problem with derivatives.
Okay.
If a stone is thrown down at 80 feet per second from a height of 1,050 feet, its height after t seconds is given by s equals 1050 minus 80t minus 16t squared.
Okay.
Find its average velocity over the period 1, 4. And then B is estimate its instantaneous velocity at time t equals 4.
Okay. To find its average velocity, we want to take its position at time 1 second, figure out its height at 4 seconds, subtract those two heights, and that's the amount of distance it will fall in 3 seconds. Distance divided by time equals rate, so that would be the average velocity. So let's figure out the velocity at t of 1. So we're going to take h of 1 is what?
So that's 1050 minus 80 minus 16.
Okay, so 1050 minus 96 must be 954. So that's h of 1. Go down just a notch here. And now we need h of 4 to figure out what its height is going to be at time equal 4 seconds. So that would be 1050 minus 80 times 4 minus 16 times 4 squared. What does we have here? This is 1050 minus 320 minus 16 squared, which is 256. So that's 576. So we're left with 474. I did my arithmetic correctly. So we go from time equal 1 second to time equal 4 seconds. We go from a height of 954 to a height of 474. So 954 minus 474 divided by 3 seconds, 4 seconds minus 1 second, gives us our average velocity. So that's 480 over 3, or 160 feet per second. (160 feet per second is the average velocity over that 3-second period. And the second part of the question was, what is the instantaneous velocity?
Yes, at at t equals 4. Okay, so now, but when it's falling from 954 to 474.
Okay, so it's minus 160 feet
Okay,
per
yeah.
second. My apologies, yeah.
No, that's okay.
Yeah, no, when you're talking velocity, down is negative, up is positive. To the right is positive, to the left is negative. So sign is definitely important here. But the key thing to know is that it's going at an average speed of 160 feet per second in a downward direction.
Okay, that makes sense.
Okay. Now, instantaneous velocity. This is what calculus is all about. Algebra allowed me to figure out the average velocity. I didn't use any calculus at all. I just took its position at 1 second, its position at 4 seconds, the distance covered divided by the time expired. That's distance equals rate times time. That's algebra. Instantaneous velocity. Well, that we can't do because instantaneous velocity would require us to divide by 0.
Right.
Right? So we have to come up with some method of doing it, and that's why calculus was invented. If you take the first derivative of this function, what do you get?
You get negative 80 minus 32t.
So h prime of t is equal to negative 80 minus 32t. And what they're saying is, what is h prime of 4? In other words, h prime being the instantaneous velocity as a function of t. So whatever t you want to plug in here, it'll tell you exactly what its velocity is. Notice that at time 0, its velocity is minus 80, which was the original premise of the problem. The stone is thrown with a downward velocity of 80 feet per second. So h prime of 4, I'm going to plug in 4 for this. I get minus 80 minus 128, which is minus 208. So its instantaneous velocity at 4 seconds is minus 208 feet per second, which is much faster than its average velocity was, as you would expect it to. In other words, it starts out at 80 feet per second, but because of gravity, it's accelerating. So after 4 seconds, it's going to be going faster than it was at the beginning or faster than it was at time 1 second. So this is a very reasonable answer to get, minus 208. We would expect it to be a bigger number than the average, 160.
Right. Okay, then. Let's move on to another simple derivative.
Okay.
Sometimes they confuse me with the placement of x. This is an example of that. Find or compute f prime of a algebraically for the given value of a. F of x equals negative 6 over x when a equals 1.
Okay. So there's 2 ways to do this. The way I prefer is to first figure out what f prime of x is. Okay. So can you use the power rule to do that?
I think so.
Yeah, because this can be rewritten as minus 6x to the minus 1. Now, using the power rule, what do you get?
6x?
6x to the minus 2.
Oh, sorry, right.
Remember, we take the coefficient, multiply it by this coefficient, and then subtract 1.
Right.
So after we subtract 1, it's this, and that's the same as this. So now I can give you f prime of a given all kinds of different a's. What was a equal to?
1.
So f prime of 1 is going to be 6 over 1, or 6.
Okay, that was easy enough.
Yeah. Once you are able to calculate the derivative function, then you can evaluate that derivative at any number you want, which is much better technique than the other alternative, which is f of x minus f of a all over x minus a as x goes to a, taking the limit of that. Have you had this definition?
Yeah, the crazy limit derivative.
Yeah, the limit quotient definitions, they're a pain. I'm a marvel at why they start calculus students off with the toughest part. It would be like teaching somebody to ski and putting them on the expert slope to begin with.
Yeah, no kidding.
So it makes things a lot easier once you've learned the power rule and the product rule and all of those. Then you can dispense with having to use the limit quotient definition.
Okay. Yeah.
Unless they make you do that. They may want to make sure that you know how to use the limit quotient definition. Like if I said f of x was equal to x squared, give me the derivative of that and use the limit quotient definition to do it. Are they liable to ask something like that?
Technically, yeah.
Okay, let's talk briefly about it then. The derivative is defined as the limit of f of x plus h minus f of x all over h as h goes to 0. That's the definition of derivative. So if I wanted to apply that definition instead of the power rule, well, I need what is f of x plus h. If f of x is x squared, then f of x plus h is what?
X squared plus h?
Well, it's x plus h squared.
Oh.
In other words, I'm going to plug in whatever's in my parentheses wherever I find x. Okay, and then that's equal to x squared plus 2xh plus h squared. So now when I plug in for here, I get the limit of f of x plus h, so that's x squared plus 2xh plus h squared minus f of x, which is just x squared, all over h as h goes to 0. And this always happens is that any term without an h in it is going to cancel. And notice what I'm left with. I'm left with 2xh plus h squared all over h, and I'm going to calculate the limit of that as h goes to 0. Well, I can factor out an h from the top, leaving 2x plus h all over h. This h then cancels with that, and when I evaluate that as h goes to 0, I get 2x, which was what I would have gotten using the power rule a whole lot quicker. But like I said, if they want you to know how to do this, they can ask questions that will force you to know that method.
Right. All right then.
Okay.
Here's something a little different.
Okay.
Find all values of x, if any, where the tangent line to the graph of the given equation is horizontal.
Okay.
The graph equation is y equals negative 7x squared minus 8x.
Okay. Let's talk about any graph. Let's talk about a parabola.
Okay.
Where is the tangent line have 0 slope? Not here. That's got a positive slope. That's got, a negative slope. That's a negative slope. There's a positive slope. There's a positive slope. There's only one place. That's at that vertex. it might seem strange to start off differential calculus and say that it all comes down to the slope of the tangent line. But that's correct, because the slope of the tangent line represents how that function is changing at that point. In other words, at this point right here, that function is not changing. Its slope is 0. Over here, the function is changing rapidly. It's increasing rapidly. So its derivative is going to be positive because the slope of the tangent line is positive. So when they give us a function like this, which is an upside down parabola, we'll say it's that. And I know that's the case because there's a negative in front of the leading term. So I'm looking for the vertex. But what I'm really going to do is I'm going to take the derivative of this function and I'm going to set it equal to 0. Because the derivative is going to give me the slope of the tangent line. And they're saying, well, where is the derivative equal to 0? Well, first of all, let's take the derivative. And where is that equal to 0? It would be...
Wouldn't it be negative 14x minus 8?
Excuse me. You're right. Sorry.
That's okay.
Yeah. So, in other words, minus 14x minus 8, I'm going to let equal 0. And that's going to tell me what value of x in the original function is the slope of the tangent line 0. Well, if I solve this, I get negative 4/7.
Okay, I got it.
So let me redraw that graph. It must have been over here. And this point right there is minus 4/7.
Okay.
And that's a huge application for calculus, because notice that the slope of the tangent line is 0 at the maximum. So if I want to know where the maximum of that function is, or any function for that matter, I can take its derivative, set that derivative to 0, and it's going to give me the maximum in that little area, even if it's a function something like this.
Okay.
Well, if I take the derivative of this function and find out its 0 points, there's going to be one there, there's going to be one there. Well, this one's a local maximum, and this one's a local minimum. So finding out where the slope of the tangent line is 0 won't always give you a maximum. What it does is it gives you an extrema. It gives you either a local minimum or a local maximum. And then there's other tests for determining whether it's a maximum or a minimum. But that process is used, that's the primary process we use calculus for, is to calculate maximum or minimums of functions.
Okay. That makes sense. All right, then. Here's a concept that I honestly never fully grasped. It's applying whether or not the hospital's rule applies, if I'm saying that right.
Yeah, I'm not sure how it's pronounced. I tend to pronounce it L'Hopital.
Huh.
But I used to pronounce it La Hospitals because it's spelled that way.
It is, yeah.
Okay,
Okay, well,
where does it apply? If I'm trying to take the limit of this, and I do direct substitution, I get 0 over 0. If direct substitution produces 0 over 0 or infinity over infinity, then you can apply L'Hopital's rule. And L'Hopital's rule says take the derivative of the numerator and take the derivative separately of the denominator and then reevaluate it. Well, if I take the derivative of sine x, I got cosine x. And if I take the derivative of x, I've got 1. And now if I evaluate this as x goes to 0, I get 1. I don't get the indeterminate form anymore. And that's basically what L'Hopital's rule says, is that if you're looking at the indeterminate form, then you can take the derivative of the top and the derivative of the bottom, evaluate it again. If you're still looking at the indeterminate form, do it again. In other words, you can have multiple iterations of L'Hopital's rule. Maybe this comes out to still be 0 over 0. Well, I take the derivative of the numerator again and the bottom again and analyze it again.
Okay. Okay, well, the question here is asking, say whether or not L'Hopital's rule applies. If it does, evaluate or use it to evaluate the given limit.
Okay.
It's the limit as x approaches negative infinity of 5x to the 4th plus 20x to the 3rd over 1000x to the 3rd plus 8.
Okay. If you substitute first of all, I don't get the indeterminate form if I substitute infinity. In other words, L'Hopital's rule would not apply here because the leading term in the numerator is that, the leading term in the denominator is that. Since this is a higher power, this whole thing is going to go to x in the numerator, and as x goes to negative infinity, this whole thing goes to negative infinity.
Okay, so it would not apply in this case?
No, because for it to apply, you have to end up with an indeterminate form. Indeterminate forms are the following: 0 over 0, infinity over infinity, negative infinity over negative infinity, infinity minus infinity. All of those are indeterminate. And these are the ones where you can use L'Hopital's rule. 0 over 0, or infinity over infinity, or even negative infinity over negative infinity.
All right. Well, it's telling me it does apply here. Yeah, it says L'Hopital's rule does apply.
Well, I suppose what they're doing is saying that if you substitute infinity here, you end up with infinity in the top and infinity in the bottom, and so you can use L'Hopital's rule. The thing is, you don't need to use L'Hopital's rule.
Right.
So maybe that's the distinction that I was not making. I can solve this by strictly looking at the largest term there, the largest term there. As long as the x to the 4th's in the numerator, this thing's going to x. In other words, this x to the 4th divided by x to the 3rd is going to be x. And I don't care about any other terms. I'm not concerned with that one or that one. So all I know is this thing's going to go to x, and as x goes to negative infinity, this whole thing goes to negative infinity. So if I want to say that, okay, it is the indeterminate form, and use L'Hopital's rule, okay, the numerator goes to 20x cubed plus 60x squared. And notice that you don't use the quotient rule here. It's easy to get the quotient rule confused with L'Hopital's rule. I'm taking the derivative of the numerator and I'm taking the derivative of the denominator. Well, now when I evaluate it, it's the same thing as I was going to evaluate before. The numerator is going to go to x because that's x to the cubed and this is x squared. So as long as the numerator goes to x, I still have to evaluate it the same way I was able to evaluate it before I used L'Hopital's rule.
Right. Okay. So just real quick, so when the exponent is larger on top than it is on bottom, it goes to infinity or negative infinity?
Yeah, it does not matter the coefficients. If I have something like this, and I say, what happens as x goes to infinity? Well, this comes down to a over b times x, right? That's what that reduces to. Well, as x goes to infinity, this whole thing blows up. So as long as the numerator is bigger, and by bigger I mean only the first term, it didn't matter that I had 1,000x cubed down here and only 20x cubed up there. The x to the fourth rules when you're going to infinity.
Right.
And if it's the reverse, this is always going to go to a over bx. And in this case, the denominator blows up, and this whole thing has to go to 0. So when your numerator blows up alone, the whole thing goes to infinity. When your denominator blows up alone, the whole thing goes to 0. The only place you need L'Hopital's rule is when both of them do the same thing. Either both go to 0 or both go to infinity. So that's the only reason I would have said L'Hopital's rule is not necessary in either one of these cases, or in this case we just talked about, because I can evaluate that limit without using L'Hopital's rule.
Right. All right then.
For instance, tell me if L'Hopital's rule applies here.
Well, you end up with 1 over 0.
Actually, you end up with 0 over 0, because cosine of 0 is 1. So you end up with 0 over 0 when you directly substitute. That's what we're looking for to be able to solve it with L'Hopital's rule. I don't have a real good method for determining this limit, to be honest with you, without L'Hopital's rule. I can't use my normal techniques for limits that you've learned to find this limit. But if I use L'Hopital's rule, what's the derivative of the numerator?
It'd just be the derivative of negative cosine. So yes, the sine over 1.
Uh-huh. And now, as theta goes to 0, this whole thing goes to 0. So 0 is the limit. It's just that I needed L'Hopital's rule to tell me that.
Okay, awesome.
Have you done much with trig functions, or pretty much everything with polynomials?
A lot of polynomials.
Okay.
And I guess what I want to work on next would be implicit differentiation.
Okay.
Find dy over dx using implicit differentiation of the equation 2x plus 7y equals xy.
Okay. The only difference, if I tell you, let's start with explicit differentiation. Okay? If I want dy dx, I only have to use the power rule, and I don't need to follow this with anything else. But if I want a dy dt, and y was x squared, well, I have to take the derivative of that, but now I have to kind of apply the chain rule and figure out dx dt. So the only thing that's different about implicit differentiation is when you run into a variable that is not your variable of integration, you have to add that to it.
Okay.
So that's what we're going to do here. Since we want dy dx, we can explicitly differentiate that part. That's just 2. And now we have to explicitly differentiate that, but y is a different variable than x.
Right.
So there's the explicit part of it, but we have to follow it with a dy dx because we ran into a different variable.
Okay.
Okay, now we're going to do the same thing to the right side. We're going to use the product rule. So the product rule says I'm going to take the first thing times the derivative of the second thing. So the first thing is x. The derivative of the second thing is is 1. But since it's a different variable, it's not x, I have to also put dy dx next to it. The rest of the product rule is now I'm going to take the derivative of x, which is 1, and multiply it by the second term, which is y. Now I don't have to follow that with a dy dx because I didn't differentiate y there.
Right.
Okay, so now my goal is to solve for dy dx, and I do it algebraically. I'm going to get everything that has a dy dx in it on one side of the equation. And everything else on the other. You with me?
Yes.
Okay. Now I'm going to factor out the dy dx. And this is something you almost always have to do when you're implicitly differentiating. And the other thing that's different about implicit differentiation is you frequently end up with an answer that is both a function of x and y. So there's dy dx. And I still have a y and I still have an x in there. And that's fine. There's nothing wrong with having both variables in your answer. If they asked us to evaluate this at a point, let's say evaluate it at x equal 3, well, I'd go back to my original function, and I know that when x equals 3, I can figure out what y is. And so I would input x equal 3 and whatever y is equal to when x is equal to 3, I would plug it in for that. So I would be able to tell you the first derivative at the point x equal 3, y equal whatever.
Okay.
But let me give you another and I say, what is dy dx?
Okay.
Notice that I'm really implicitly differentiating this. In other words, I'm really taking the derivative of that and getting 1 and then adding the dy dx after it. So now we need to implicitly differentiate the right side of this equation.
All right, so you end up with, so I can explicitly differentiate x.
Well, I can do that, and then if I want, I could even follow it with a dx over dx. But that's always 1, so I don't need to write it.
Right.
Okay.
So,
now I explicitly differentiate the r variable, but since it's r and not x, I have to put the chain rule in there and do that. So that would be dy dx.
okay.
and then I might have some other equation that relates r to x so that I could figure out what dr dx is and fill it in there. And that's usually the case. When you're implicitly differentiating, you have other equations that allow you to state what r is as a function of x, which allows you to come up with dr dx.
Okay, awesome.
Okay.
Just real quick, will you be available again tomorrow if we wanted to do a second session?
Sure. After I got a golf game at 9:30, I'll probably be home by 2, so maybe 2:30 or 3?
Yeah, 3 should work fine. I got a doctor's appointment at 1, so 3 should work perfect.
Okay, let me go ahead and put you down here. In fact,
let me get my phone. I'll put it in there too.
Okay. Oh, this always puzzles me. Okay, so that's online from 3 to, I'll put 4:30 down here, and you can quit whenever you want. We don't necessarily, I don't have a lot going on in the summer, so I got lots of flexibility in the summer. I just have to mainly work around golf and some morning appointments there that I have.
Okay, cool.
Okay. And then you'll already have GoToMeeting on your computer, so the only thing I'll do tomorrow is text you the meeting ID. I won't need to call you. I'll just send you a text with that meeting ID and go ahead and open up GoToMeeting and put in that meeting ID. You know what I'm saying?
Yeah, I understand.
Okay. Is it Robert or Bob?
I go by Robert. My dad's also Robert, and he goes by Bob.
He's the one that uses the Bob, huh?
Yeah, so to avoid a confusion, I go as Robert.
Okay. Did you have another function that you want to implicitly differentiate?
Yeah, we might as well just do the next example.
Yeah. Now there's some places where it's almost impossible to explicitly differentiate something because you can't define it as a function of y. You know what I'm saying? If I had y cubed plus y squared plus y equals x, and I said differentiate that, well, I would not be able to define that. I would not be able to solve that as a y equals. So I really wouldn't have any other way to differentiate this other than implicitly. And the way I would implicitly differentiate it would be this way. By differentiating both sides of the equation, I get that. Now I factor out the dy dx, and whatever I end up with is going to be my answer. So, all right, what one did you have?
Okay. E to the x times y minus y equals 1.
Okay. This one we could actually solve for y, easy enough, by factoring it out, and then explicitly differentiate it. But rather than go to that trouble, I don't need to. I can just implicitly differentiate it from the start. So let's deal with this first. So what does that give me?
Let's see. The derivative of e to the x is e to the x, isn't it?
Uh-huh. So there's the first term of the product rule. Let me put parentheses around this. And I don't need a dy dx because I didn't differentiate the y term yet.
Right.
Okay.
Okay, and then the second part of the product rule would be e to the x dy dx?
Yes. Okay. And now this part. So what's the derivative of y?
Dy dx?
Right. And what's the derivative of 1?
0.
So now how are we going to solve? I can remove these parentheses, they're not needed. Now what do I do from here?
Get the dy dx's on the same side.
Okay, and take everything else to the other. So I'm just going to take that first term to the other side, put a negative in front of it, and erase it from this side. Now I've got this. Now what? Now you want to, there's always this step, which is to factor out the dy dx. What's left behind? In other words, I'm factoring just the left side of this equation.
What's that?
So after you factor out the dy dx, what's left?
E to the x.
E to the x minus 1. So now that's all equal to this. So if I'm solving for dy dx, I just divide everything by that, and there's my answer.
Okay, awesome. And then the second part of the problem says, compare your answer with the result obtained by first solving for y as a function of x and then taking the derivative.
Okay. To solve y as a function of x, I'm going to factor out a y. So I'm going to have y times e to the x minus 1 equals 1. So if I solve for y, I get 1 over e to the x minus 1. So there's y. And let's see if we get this same answer. Notice that we're going to get an answer that's just a function of x, whereas this is a function of x and y. But notice that if I want, I can go back over here and substitute for y this expression. I didn't do it in the first case because we never solved for y. And it's not always necessary to go back and substitute for y. So let's go ahead and figure out y prime. Y is equal, if I rewrite this like this, then y prime is equal to what?
Let's see, so y prime is equal to, okay, so we change all that, right?
Yes.
Okay.
So it's negative 1 times e to the x minus 1 to the negative 2 times the derivative of the inside.
Which is just e to the x.
Okay, so there's my y prime, and what I'm saying is that's the same as this. Well, for me to prove it, I have to go back and substitute for y over here. Well, we solved for y. It was equal to 1 over e to the x minus 1. So on this becomes minus e to the x times 1 over e to the x minus 1. Is that your dog or my bark? Do you have a dog?
Yeah, that's my dog.
That's your dog.
Yeah.
Because that sounds exactly like my dog. That happens a lot, and I can never tell whether I'm...
Yeah, we got a little Chihuahua. She doesn't know she's little, though.
Yep, I had a teacup poodle that was like that, and now I got a small terrier that's about 10 pounds.
Yeah.
They'd never know they're little, yeah.
Yeah, I think about like 5 pounds, 6 ounces.
Yeah, so, wow, that is little. Although my teacup poodle used to be 4 pounds. I had a 4-pound dog for a long time. She lived to be 16, too. So, yeah, they can live to be ripe old ages. So what I'm saying is that those two are equal. This was determined from explicit differentiation. This was determined from implicit differentiation, which I then went back and substituted what y was equal to get it as 100% a function of x. And I don't know if you can see that why these two are equal or not. Notice that this denominator that's in the numerator is going to go with this denominator, and I'm going to end up with e to the x minus 1 squared, which is that term. And then the numerator was minus e to the x, which is right there.
Okay. That makes sense.
Yeah. This step where I substituted for y, that isn't always necessary, because a lot of times they'll say evaluate the derivative at a coordinate, where they'll give you the x and the y coordinate, in which case if I wanted to figure out what f of 2 comma 3 was, then I would substitute x of 2, y of 3, and come up with a number. And that would be the slope of the tangent line at that coordinate.
All right. Now, I guess the next thing I'd like to work on is I want to spend a lot of tomorrow's session working on integrals.
Okay.
Because that's going to be a bulk of the test. But right now, what I want to focus on is consumer surplus.
Okay.
Calculate the consumer surplus at the indicated unit price P for the demand equation. The demand equation is P equals 18 minus 2Q, and then P with a little dash over it equals 3. So the unit price.
So P okay, I'm not up on my economics here. So this is the demand equation, where P is the demand. If you take the first derivative of the demand equation, you get the what is called the cost of the next unit of production, basically.
Okay.
I think that's what you're talking about here. So if I take the demand function and take the derivative of it, I just get minus 2. There was no exponent on the Q?
No, there's not.
Okay. I'm not sure what they're looking for here, to be honest with you. Do they have an example anywhere on your consumer surplus?
Let's see.
Did I even write this correctly? Is that the way it's written on your paper?
One second. Yep.
So, because that normally means the mean. That horizontal line means the mean is 3. I honestly don't know what to do with this. I'm not sure exactly what they're stating with this information. I understand the demand function, but this what right here, I don't know what that is. In a statistics interpretation, that would be the mean of the function.
All right.
Maybe we could, if you could find an example of one of these, and we can look at it tomorrow and see how they do the example, then we can probably figure out how to do this.
Yeah. Here, I'll send you this this screenshot of their definition.
Okay.
For consumer surplus.
Okay.
Maybe that'll help.
Consumer surplus?
Yep. Hopefully that clears something up.
Okay. Difference between what consumers are willing to pay and what they actually pay is called the consumer surplus. If the demand is given by that function, the selling price is that, and Q is the corresponding demand, then the consumer surplus is the difference between willingness to spend and actual expenditure. Okay. Now I think we can probably figure out what to do. I tell you what, can you let me cogitate on this, and we'll pick up on this particular problem tomorrow?
Sure, that works.
And that way I don't need to waste 15 minutes of your time figuring it out on your time.
Yeah, that's okay. I think we're at a good stopping point. We got a lot done.
All right, let's do that. And then that'll give me the evening to study this, and I'm sure we can figure out how to answer that question.
Okay.
Looks like it's going to be just plugging in and solving.
Yeah.
They're giving us P. What is that called? The selling price they've given us is 3. Mm-hmm. And so the only thing we don't know is this Q, the corresponding demand, and they must tell us how to figure that out. All right, I'll look at it tonight.
Okay. So how does this work for me to pay you? How do you do that?
Well, the easiest way is if you have a PayPal account. That's
let me ask my mom if we do.
Okay.
All right. And Mr. Cohen, I got my mom here, so...
Hi.
What do you have another method besides PayPal?
Yeah, you can certainly send me a check in the mail. I have no problem with that. And this is the address.
Oh, okay. Because I have used the PayPal. I just have to go on and figure out how to do it.
You're welcome to eat whatever's easiest for you is fine with me.
Okay. Well, maybe I'll just write a check because I had to write a check for something else too, and I go.
Okay.
Okay.
Yeah, PayPal, typically you need to fund it, and then you can make payments that are kind of immediate out of it. But if you haven't used it in a while, it probably doesn't have a balance in there. So it might be a pain for you to, it might take a while to fund it. So, yeah.
No, I've never done it like that.
Okay. Well,
would it be easier if we just sent you one check after tomorrow's for like the combined amount of days?
Sure, that's fine with me. Absolutely.
Okay, cool. I think we're just going to do that.
Okay.
You want to... Right here. Right here. Then just page up.
So if we did an hour and a half tomorrow, the total would be 80.
80?
Because it's 32 per hour.
Okay, perfect.
And the first half hour today was free. So.
Thank you very much.
Oh, that's fine. I just do that as a standard practice. So.
Well, that's very nice of you. Okay, so then after tomorrow, it'll just be a total of 80.
Yes. That's assuming we do an hour and a half tomorrow.
Okay.
Awesome.
Okay?
Thank you very much.
Okay. Yeah, so I will talk to you, Robert, tomorrow at 3. And like I said, I will just text you the meeting ID number. And you should have an icon on your desktop now that looks something like a little flower. And so when you want to join a meeting, just click on it, double click on it, and it'll ask you for a meeting ID. You don't need to go back to that website every time.
Okay, the number I gave you earlier was actually my home phone number. So would you like my cell so you can text me the meeting number?
Yes, I would. Let me put that in there. What's your cell?
720 940 5861.
Okay, that's the one I'll use from now on.
Okay, awesome. I will see you tomorrow at 3 then.
Okay, Robert. Thank you.
Have a nice day.
You too. Bye-bye.
Bye-bye.